All right, let the fun begin. So, one of the hardest parts of intro chem is naming, particularly in this class because they decided to do all the naming in one chapter all at the same time, right in the middle of our exam. So we have a huge mountain of information to climb. The best way to handle this is give you a couple patterns, and hopefully that you can use those patterns, use those trends to do things a little bit quicker than just brute force memorization and mountains of flashcards and so forth. So the disadvantage of chemistry is there's lots of known chemicals. Some of them have common names like water is H2O or ammonia is NH3, or even the heroic laxative used in the Civil War to keep people from, filling their underwear, calomel, which was a heroic laxative to clean them out before battle. Some things just have a nickname, just like people have nicknames. So those are great, but is there a systematic way to learn to recognize a lot of these ingredients and a lot of our food items that we tend to eat? And that's what we're after in this particular chapter. So one of the first categories of compounds we're going to cover is binary. So anytime you hear the word binary, hopefully you think of something like a bicycle. So binary definitely means two. And that just tells you there's two elements that are going to have to be named in this particular compound. There could be subscripts of various numbers, but what matters is there's only two capital letters. There's only two elements to deal with in these kinds of compounds. So if you're doing binary ionic, so binary meaning two, ionic means metal with a nonmetal. Metals tend to be positive cations, and nonmetals tend to be negative anions. And this is what we see down here with these examples with lithium chloride, magnesium chloride, and iron oxide. We'll learn how to name some of those. More recently, we watched a video, hopefully, over binary covalent, and that's when you have two elements, but now both are nonmetals. And if both are nonmetals, this is where we're going to have to share electrons through those Lewis dot structures in order to make them, or in order to draw them. These are a little bit easier for most students, and that's because we're using prefixes. So something like carbon monoxide or nitrogen dioxide or silicon tetraoxide, using those prefixes to know how many of each atom to write down or to draw, versus using charges and crossing charges like the crossover rule would imply for those that are binary ionic. So in naming anything binary, notice the ending of the name is very predictable based on what we'd expect to hear from compounds, and that's this IDE suffix. So IDE is going to be binary in almost all situations. There are a few exceptions, but almost always binary is IDE. We do see things like cyanide or hydroxide that do end up having IDE, but aren't binary. But for the most part, 95% of the time, IDE is safe to say that there's only two elements. And they either have prefixes to know how many, or they have charges to cross to know how many. So this should bring back some memories from the end of exam 1. Once you see that sodium is in group 1, you're going to take that charge and then you're going to cross it over. Once you see that sulfur has a -2 based on its family 16 needing 2 more electrons, you're going to cross it over and you get an A2S. Notice the first name, sodium, stays the same. Sodium is sodium. It is the sodium ion, technically, but in this case, just sodium is fine. And then instead of saying sulfur, notice we say sulfide. Magnesium, you cross the 2, you cross the 1, you get MgCl2. But again, in the name, you just see magnesium for magnesium, and then instead of chlorine, you say chloride. Aluminum, group 13, cross the 3. Oxygen, group 16, cross the 2. That would have taken, some memories from back in exam 1. We get Al2O3. Aluminum for aluminum, even though there's 2, still aluminum, and even though there's 3, still oxygen turns now into oxide. And then lastly, if we have 1 from group 1, we cross it. Group 15 has 3. We cross it, we get Li3N, but again, the first name is always straight off the periodic table, no changes. That's not going to be the issue in your homework. In your homework, the issue is going to be, does it end in IDE? If so, probably binary, check. Or it could give you choices of ATE or IT, and those are ternary compounds that we'll learn about coming up in a little bit. So pay attention to IDE. You're pretty safe to recognize binary. You're pretty safe to recognize 2 elements, 1 metal, 1 nonmetal here for ionic compounds. Remember to cross charges. If charges are the same, you don't have to cross them. If you do, you have to reduce them. Even if you cross, say, a 4 and a 2, make sure you reduce those to a 1 and a 2 and so forth. So always reduce charges when possible, especially for even numbers. That's going to be possible. And then just make sure that you use the name for the first element, usually the metal. It's going to have its name straight off the periodic table, no changes. And then as you get to the nonmetal, just remember to add that IDE ending from its elemental name straight away. One of the difficulties with binary compounds is when we start adding in transition metals. Transition metals have a disadvantage that some of them are very old, some of them are Latin-based, some of them have Latin names. So they ended up with Latin suffixes of ic versus os. Anytime we have ic versus os, ic is always the higher charge, os is always the lower charge. So the example here for ferrous versus ferric, notice os for ferrous, that's a +2. Ferric, that's a +3. So ic is always the higher charge. We're still going to cross charges, no different than before with these transition metals, and even up here we're going to cross charges, no different than before. But notice their formulas are different, and their formulas are different because the metal ion is different. So we see that for iron, it has an ic and an os. We see that for copper, that's cupric and cuprous, cobaltic and cobaltus, stannic and stannous, plumbic and plumbus, and then it used to be mercuric, mercurous now, but it used to be hydrogyrous and hydroguric. Notice very unique is mercury 1, mercurous. That's actually a 2/2 polyatomic cation. That one is super unique. It'll answer 2 of your homework questions, actually. All of these are listed in the supplemental experiment 6, kind of on that right side column. So is there a way to kind of take away some of these and think about them to make them a little bit easier to think about in the sense of patterns? Let's show you a periodic table and show you that there is a little bit to recognize just based on their location. So if we were to look at, say, iron, cobalt, and nickel, this group here, iron, cobalt, and nickel, these guys like the +3s and +2s. That's what they transition between. Turns out silver likes a +1 only. Cadmium likes a +2 only. Zinc likes a +2 only. And notice this idea with silver. If silver likes a +1, so does copper. The disadvantage of copper is it likes a 2 and a 1. So +2 and +1 is pretty common for a copper. Mercury actually has a +2, which is predictable based on the zinc and the cadmium ions above it. But it also has a mercury 2 atoms over +2 as well, which is actually mercury 1 when you reduce 2/2 to 1. So that's even weirder yet. In group 14, we'd expect 4 valence electrons, and that tells us that the tin and the leads, they're going to like +4s, but they also like +2s. So the take-home message here is, with the exception of silver, silver is a +1 only, so +1 only, but everybody else has a +2. Iron, cobalt, nickel have a +2. Copper has a +2. Zinc has a +2. Cadmium has a +2. Mercury has a +2 and another weirder +2/2. And even the lead and tins have a +2. So everybody has a +2 with the exception of silver. That tells you that really what they're losing is just these 2 electrons. They're losing 1 electron here, 2 electrons there, and then leaving their d electrons alone. So that's why they have +2s in many cases. Tin and lead can also lose the next 2 electrons. That's why they're going to have +4s. The rest of them are pretty weird, and it takes Gen Chem level of understanding of electron configuration to understand why they're doing what they're doing. But suffice it to say that they are just kind of descending in charge. So the 3s are kind of in the middle, the 2s are on the edges, and then the 4s over in the group 4. So they do have some slightly predictable locations to help you realize that you may not need flashcards if you can just recognize positioning of some of their charges. So Latin names are getting pretty old. And if you look at a lot of Doritos or beef jerky packages or Skittles, you're going to see a lot of these preservatives using those old Latin-based names, the ic and the os still, which is why we have to still cover them. More recently, we've converted the Latin system into what we call the stock system. The stock system is a whole lot nicer because we actually use in parentheses the charge of the actual cation. So there is no guesswork of who's a 3, who's a 2, who's a 1, who's a weird 2/2 like mercury. In the stock system, if you want iron 2, they literally say iron Roman numeral 2. If they want you to use iron 3, they say use iron 3 by giving you Roman numeral 3. So the stock system is new. And unfortunately, because it is so new, those really old companies like General Mills that make cereal, they're not with the new times yet and haven't been using these probably like they should. So we're forced to learn both, which is to our disadvantage. But in both cases, we are still just crossing charges. Notice after we cross charges to the two elements, we still end in IDE. So none of that's really changing. What is changing is listing the charges in parentheses for stock systems or adding the ic versus os in those Latin system kinds of names. So here's an example. So let's try to dissect this one so that you can better dissect some of your homework in a similar fashion. And then we have a big lab coming up that'll also help with this as well. Give you some hands-on practice there, at least busy work practice anyway. So we have titanium, we have chlorine. So one thing that we taught you very early in this semester so far is that if you have a formula, you cross charges down. So if you cross charges down, why can't you not then cross them back up? So if that 4 came from titanium, why not give it back? And if this imaginary 1 came from chlorine, why not give it back? That tells you that titanium is a +4 and that chlorine is a -1, because when you cross those charges back down, you would get the formula TiCl4, like we'd expect, say, on the end of exam 1. So how do we name it? That's this chapter. We've already done this crisscrossing idea. That was the previous exam and about 2 chapters ago. But now it's a matter of how do we deal with naming these new compounds. Is it titanic or titanus? Is it titanium 2 or titanium 4? Well, we know that answer now. Now we know that because this 4 came from this 4, which is really just this 4, that is titanium 4. And if titanium is 4, that's just titanium IV. And if there's a titanic and a titanus, different from the ship, of course, titanic would be a high charge. We said earlier that everybody has a 2. If everybody has a 2, but now we see titanium had this magical 4, that tells us it's probably its high charge. So we would call that then titanic versus titanus, which would be a +2 titanium. Lastly, we have chlorine. So instead of saying chlorine, we would say chloride, and that's because it's binary. So that just repeats itself for its Latin name. So a lot of companies are still going to use the ic and the os, which is unfortunate. They're just really old and not with modern times when it comes to a lot of their ingredients for their preservatives and a lot of their food products. If a new company were to pop up tomorrow, it's a good chance they would use the new system because they wouldn't be stuck in their old, early 1900s kinds of nomenclature ideas. So the take-home message here for binary ionic is first name, straight off the periodic table, unless you're a transition metal. Then you have to worry about stock versus Latin names. The non-metal, always ending in IDE. So that IDE is a great takeaway, a great clue for binary. As we get to binary covalent, a little bit easier just because covalent's going to use prefixes. And most of these prefixes you've probably seen before, especially if you've taken a driver's exam. If you have one, it's mono, just like the disease, so to speak. Di. 2, tri, like a tricycle has 3 wheels. 3, tetra, like the game Tetris that has 4 lines to get maximum points. 5, penta, pentagon has 5 sides, just like a school crossing sign. Hexagon, 6. 7, heptagon. 8, octagon, so whether you like cage fighting, MMA kinds of fighting, or if you like running stop signs, same kind of idea. Octagons there, nonagon, decagon. So most of these won't require a huge amount of rememorization to deal with. We're just using them literally for the subscripts. And the second more electronegative element is going to end in IDE, just like the other binaries that we saw. So notice in this one we see hydrogen. Hydrogen is less electronegative at 2.1. So we always put those less electronegative elements out front. And that's why hydrogen is out front. So again, it was 2.1 in electronegativity. Chlorine was 3.0. So that's why we position them one in front of the other. But most importantly, notice hydrogen still just like it is off the periodic table, right? Hydrogen is hydrogen. Even though this is the hydrogen ion, we're still calling it hydrogen. But instead of chlorine, again, we call it chloride. So this name, always the same, just like it was for metals. If there were, say, 2 hydrogens, we would say dihydrogen chlorine. If there were, say, 2 chlorides, we'd say hydrogen dichloride. So we literally just use those prefixes to tell us how many. It's just kind of redundant sometimes to say monohydrogen monochloride when it's not that necessary to say when there's one. Kind of a little redundant in that kind of capacity. So not always is mono used. If mono is used, it's usually for the second element, but not always. So in carbon monoxide, we use it, but here with hydrogen chloride, we don't say hydrogen monochloride. Just seems a little weird running off the tongue, I guess. Here's 2 examples. We see sulfur, so we write sulfur. No big deal there. Sulfur is sulfur. You can find that on the periodic table. But as soon as we see 6 fluorines, notice we say hexa, and then it's fluoride. Same thing with nitrogen. Because we have 2, notice we said dinitrogen. And then when we have 4 oxygens, we said tetra, or in this case, tetroxide. So they lost the A just to make it roll off the tongue a little bit easier. But again, you're not going to be worried about a spelling test on the multiple choice or the matching of the homework. You're just going to be recognizing that 2 is di, 4 is tetra, and those kinds of capacities. Then we get to ternary, and ternary is a pain because there's so many different combinations of oxygen, so many different charges that are possible, so we're going to pick that up in a separate video.